Hello, good day. My name is Mark Gabriel B. Cuenta, and I'm going to explain the experiment 8 in simulation. So, experiment 8 is more on the QPSK using Simulink. So, the QPSK or the quadrature phase shift keying is a variation of the BPSK, and it is also a double-sided or double-side band suppressed carrier or DSBSC, which modulation scheme which is sent to 2 bits of digital information at a time, which is called the bits. So instead of the conversion of the digital into a series of digital stream, it converts them into a bit pair. So this decreases the data bit rate to half, which allows space for other users. So there are two types of this or two process, which is the modulation process and the demodulation process. So let's move on to the QPSK modulator. So this QPSK modulator circuit uses a bit splitter, two multipliers with local oscillator, a 2-bit serial to parallel converter, and a summer circuit. So following this block diagram, so at the modulator input, the message signal even bits, or the second bit, fourth bit, and sixth bit, and odd bits of 1, first, third, and fifth bits are separated by the bit splitter and are multiplied with the same carrier to generate an odd BPSK called a PSKI and even PSK called PSKQ. So the PSKQ signal is anyhow phase shift by 90 degrees before being modulated. So the QPSK waveform for the two inputs is the following. And so which shows the modulated results for the different instances of binary input. So showing the carrier or channel signal as a sine wave and the modulated result. So moving on to the QPSK demodulator, wherein the QPSK demodulator uses a two-product demodulator circuit with a local oscillator, two bandpass filter, and two integrator circuit, and 2-bit parallel to serial converter. So on the right side shows the diagram for the same circuit. So the two product detectors at the input of the demodulator simultaneously demodulate the two BPSK signals. So the pair of bits are recovered here from the original data, wherein these signals are processed and passed to the parallel to serial converter. So So the concept for this following. So these are the phase difference between signals. So it can be illustrated by the time plot shown on the next page or this page. So the phase shift signals are in the solid blues sinusoids and the original signals are the dashed black sinusoids. So here there are 4 different phase shifts shown. So the 45-degree angle or the 45 degree, the 135 degree, the negative 45 degree, and the 135 degree. So moving on to the concept for the quadrature phase shift keying. So the QPSK, this is the phasor diagram with a binary input of 0, 0, 0, 1, 1, 0, and 1, 1. So for the binary 0, 0, we have a negative 135 degree, binary input of 0, 1, a negative 45 degree, and binary input of 1, 0, a positive 135 degree, and a binary input of 1, 1, which is the positive 45-degree angle. So here in the phasor diagram, we can see the different output. So for the 1, 1, which is positive and positive x and positive y, we have positive cosine plus sine omega t, ct. So in this, we assume a 90-degree phase shift. So here in the 1, 0, a positive x and a negative y are positive y and negative x. As we can see, a cosine omega ct minus sine omega ct. On the third quadrant, the 0, 0, which is negative x and negative y axis, wherein we can see the negative cosine omega ct minus sine omega ct. And lastly, the negative or the 0, 1, which is the negative y and the positive x as shown in the fourth quadrant. So negative cosine omega ct plus sine omega ct. So moving on to the concepts. Again, this is the model used in the sine link. So we used a sine wave which consists of the 0-degree, 180-degree, 90-degree, and negative 90-degree. And two pulse generator, which is on the top side is the MSB or the most significant bit, and the lower side is the LSB or the least significant bit. So in the first or the top side, we can see the 0-degree and the 180-degree alongside with the MSB going to the switch. So after the switch goes to the sum. And on the lower side, the 90-degree and negative 90-degree alongside with the LSB or the least significant bit going to switch 1 again. So going switch 1 going to the sum. So both switch to the sum, then goes to the MUX. So the MUX shows again the reference signal. So combine them and goes to the scope. So these are the result. So in the following activity, so in this activity shows that we will zoom in on the signal for each time segments. So measure the phase difference and tabulate your answers on the table. So there are table on the data. There's a table on the data sheet that we need to follow. So first, the time segment of 0 to 0.1, 0.1 to 0.2. Then, so again, 0 to 0.1 is a 45-degree. Then 0.1 to 0.2 is an 135-degree. 0.2 to 0.3, a negative 45-degree. 0.3 to 0.4, a negative 135-degree. And 0.4 to 0.5, a 45-degree angle. And 0.5 to 0.6, a 135-degree. 0.6 to 0.7, negative 45-degree. 0.7 to 0.8, a 135-degree. 0.8 to 0.9, another 45-degree. And a 0.9 to 1, which is a 135-degree. So, conclusion. So, in this experiment, the generation and the modulation of the quadrature phase shift keying are successfully analyzed and demonstrated using the given block diagram through a MATLAB Simulink simulation. So this study showed that the Qpsk transmit 2 bits per symbol by dividing the input data into in phase or the I and quadrature to the Q components. So which modulate the two orthogonal carrier signals separated by a 90-degree phase shift. So producing 4 distinct states or phase states, the simulation results confirm that each D bit corresponds to a specific carrier phase shift, thereby validating that information is encoded in the signal's phase rather than its amplitude or frequency. So at the receiver, coherent detection using the product, the modulators, filters, and decision circuit effectively recovered the original bit pairs, and the parallel to serial conversion accurately reconstructed the transmitted data stream. So this is my proof of performance of this activity. So let's skip there. As we can see, we did the block diagram demonstrated to us in the datasheet or the PTS. So again, I use a dashboard scope to see the output data without clicking the scope. So there we change the values. So this is the scope. And on the lower side, as we can see, the dashboard scope. Yeah, on this lower side. So that is all for this experiment 8. Thank you for listening.